deep network optimization is complicated. To give a few examples, to train an image classifier, you'd use SGD with tune, weight decay, and momentum. But to train an RL agent, you'd use ADAM. And to train a GAN, you'd use ADAM, but you'd switch off momentum, and you'd use separate learning rates in the generator and discriminator. In short, there are various heuristics, and there's lots of hyperparameter tuning. So what's going wrong? Well, neural networks have a lot of structure, but popular techniques ignore this structure and operate on a flattened weight vector. The goal of our paper was to design an optimizer that works out of the box by accounting for the neural network structure. We call this neural architecture-aware optimization. We account for both the optimization domain and the smoothness structure of the artificial neuron. For optimization domain, we take inspiration from homeostasis in neuroscience and normalization schemes used in machine learning, and apply two constraints to the neuron. The first is referred to as balanced excitation and inhibition, and the second is a hyperspherical constraint. If a neuron satisfies both these constraints, we say that the neuron is balanced. As for smoothness structure, we consider perturbing the weight vector of the neuron. And based on recent results about the trust region of neural networks, we make small relative updates. And we call these updates per neuron relative. Putting these building blocks together, we get the Nero optimizer, which performs projected gradient descent over networks of balanced neurons, and it makes per neuron relative updates. Now, a per neuron relative update to a hyperspherically constrained neuron is actually just a rotation by a small angle. So we say that Nero is the neuronal rotator.
We first tested Nero's ability to train very deep neural networks without batch normalization or skip connections. Nero could successfully train a 100-layer MLP on MNIST. We also benchmarked Nero against alternative optimizers across 6 tasks, including image classification, natural language processing, image generation with GANs, and reinforcement learning with PPO. And our main finding was that out of the box, Nero beat SGD, ADAM, and LAM on 5 out of 6 benchmarks. As a direction for future work, we are excited by the idea of neural architecture-aware regularization. Modern neural architectures employ gain parameters that multiply the output of neurons. We experimented with regularizing just the gains towards 1. Our ImageNet experiments showed that out of the box, Nero outperforms unregularized SGD, and Nero with gain regularization matched the performance of SGD with tuned weight decay. In summary, we proposed the Nero optimizer that respects the neural architecture and works out of the box across many tasks. In future, we'd like to further explore the idea of neural architecture-aware regularization. Our code is available on GitHub.